Let's see. Can you see the desktop? Is everybody there?
Yep.
Yeah. Zoom forced me to do an update just a second ago, so I was like a minute or two late because it decided that I probably because there's been a lot of security. Let's see. What am I doing here? Oh, now I'm lost. Oh, brother. Zoom updated itself and it changed its interface. Now I'm lost. I hate it when programs update themselves. Yeah, now I'm not I can't even find the chat now. Oh, let's see. Okay, it's got its own button now. But, huh. I used to be able to tear off the chat. What are you seeing right now?
Huh. I have all the participants on one bar on the right. Your desktop would normally appear in a window pushed slightly off to the left.
What are you seeing as my desktop?
I don't see your desktop right now.
You don't? Wow. Okay. Yeah, Zoom has changed its interface. Oh, I hate it when they do that. Yeah, they changed it. It updated itself when I start. Okay.
There should be a button at the bottom of your screen on a black bar.
Yeah.
That says share screen.
Yeah, I see that. That's where it used to be. I was trying to bring up the chat, and I click on the chat button, and I get a chat. It used to be a tear-off window. I could put it on my other monitor, and now it's kind of attached to everything. Let me just.
It
You
will
see my
do that
desktop
when
now?
you're in full screen mode. You'll have a tear off chat, but if you're not in full screen mode, it will give you an attached chat and participant list.
Okay. Let's see. What do you see now? Do you see my desktop now? Okay.
No, it's the same thing.
Okay. Oh, wait. Okay.
Oh, there it goes.
Okay.
No,
Yeah, there it is.
Okay. Now you see my desktop.
Yes.
Okay. Maybe I think I'm back to where I should be. Oh, okay. Now, okay. There's the chat window. Okay. I got participants. I get two different lists of participants. Okay. All right. Okay. I think I'm back to normal now. Okay. Okay. I think I've got myself reorientated. Okay. So we'll play around some more with Scheme, and then we'll go back to talk to. We're using Scheme as a better language 8. You know, we really want to look at our interpreter for language 8, but I thought if we did looked at a real language that does what language 8 does, it would be a little bit more meaningful than just using our kind of baby language. So Scheme is the closest real language to our baby language because our language was modeled on Scheme and Lisp. Okay, so I thought it was good to look at some real Lisp, real Scheme programming. Okay, now here's the script that we were working on the other day. I had some goofed up parentheses. You know, the code. This is the code that was causing trouble. Boy, I had some goofed up parentheses. So I did something that uh, I switched to using square brackets. This is actually kind of a relatively recent feature of Scheme. They let you use square brackets in place of parentheses. Anywhere where you can use parentheses, you can use a square bracket, and it lets you alternate between square brackets and parentheses, and sometimes makes your code easier to read. So, for example, a lot of people in a cond will put square brackets around each clause of the conditional. Okay, so we had these notes that like gave the syntax for cond. See, people instead of doing the traditional scheme of putting a parentheses around the pairs of Boolean expressions, put square brackets around them. Okay, so the square bracket helps offset in your eye where the different pieces of the conditional are. So I had gotten lost in the parentheses the other day. So I had the code was essentially right, but the parentheses were all goofed up, and it took me a little while to get them straightened out. So here's the code we were trying to write that would add two lists up into where the list disagreed in length. So like if you added this list to this list, it would add the first two items in the list and drop the third item of this list. If you added this list to this list, it would add up the first two and drop these two items here. Okay, and the code was pretty much what we had the other day, just with the parentheses figured out. You're adding this list. Remember, X's is a good way of saying that that's a list. There's no types in Scheme, so you don't declare the type of the parameters. So instead of just saying X and Y, people do X's and Y's when they're thinking of this is a list and this is a list. Okay, so if either list is empty, we return 0. Else, we add the car of this list to the car of that list, add up the first item of each list, and add that to the recursive call on the rest of each list. So it's pretty straightforward. Just getting the parentheses balanced up is the problem. Okay, and it, can open that in Scheme. Okay, and it runs fine now. Here's the code, and here's some tests of it built into the file here. So you can run it. Okay, and there are the outputs. Now let's there's another practice problem. Let's make a slight change to this one. Notice that this is very close to be, if I make a little change to this, I can make this into the dot product. Okay, so for example, if I'm going to copy and paste it, and just want to show you can make it's easy to make this into the dot product. Okay, the dot product of two lists. Okay. Okay, remember the dot product of a list would be if you dot the list 1, 1, 2, 3 with the list 3, 4, 3, 4, 5. Remember what that means. That means 1 times 3 plus 2 times 4 plus 3 times 5. Okay, so that's the dot product. Okay, so you take the term-wise product of the components and add up the results. Okay, so we can turn this function we worked on the other day into fairly easy turned into dot product. Right now it's just adding everything up. To turn it into dot product, all you have to do is change this thing to the product of, I'm sorry, you're going to add up the product of car of S with car of Y. Okay, that little change there, that should be it. So you're going to add car of X, the sum of car of X, the product of car of X is with car of Y's. So that's this term here. You add up that term with the dot product of the rest. Oh, and then this should be dot. Okay. So to do the dot product, you would just take the sum of the first two items, the product of the first two items, take the first item from here, the first item here, take their product, and add to it. Essentially, another way to think of this is 1 times 3 plus the dot of 2, 3 with 4, 5. Okay. Okay. So it's 1 times 3 plus 2 times 4 plus 3 times 5, which here's the recursive way to think about it. The dot product of this guy with this guy is you take the product of the first two plus the dot product of the cooters. Okay, so there's the cooters and there's the cars. Okay, so you can check that there's no little typo in there. Okay, so I didn't make any typo in there. Then add some tests. We can take the dot product, okay, take the dot product of 1, 2, 3 with 4, 5, 6. Oh, and yeah. Remember, I have to quote these. These are the inputs to the function. Remember why I'm quoting them. If I don't quote them, Scheme will think, oh, I have to evaluate the arguments to dot. So Scheme would say, you didn't quote them, so it should evaluate the argument to dot. It'll treat 1 as a function and say 1 is not a function that takes parameters 2 and 3, so it'll blow up on us. So I want this to be a data vector, a data list, not a code list. See, that's the key idea in the Scheme language, is that every list is both code and data. And by putting a quote in front of it, you're saying it's a data list, not a code list. And this whole thing is a code list. This is the code list that says call the dot function on these two data lists. Okay. And let's see, what would be another example? I could take the dot of, now our dot product doesn't require them to be the same length. So I could take the dot of 1, 1, 1, 1 with, okay, since the way we wrote it, normally you take the dot product of lists that have the same length, but in our case, because of this case here, if either one of them is empty, you just stop. This should work. Okay, so do we get the right answer? So for 32, that would be 1 times 4 plus 2 times 5 is 10, that's 14. 14 plus 18 is 32. And then this would just give us 3 plus 4 plus 5. It gives us 12. Okay, so we got the right answer. Okay. One thing we should do is you should always test things on boundary conditions. Like, did I do the right thing if I do this? What should be the dot product of an empty list?
0.
Should be 0. You hope it doesn't blow up. Yeah. The idea is that if you've got some kind of off by 1 error, you could be blowing up when you give it an empty list. So, okay, so we got the right thing. And then if you're really careful, there should be 2 more tests I do here. Notice I did it with the first list being empty. Well, I should also worry about what happens if it's the second list that's empty, not the first list. Don't assume just because you've made one of them empty, you don't have a problem. You should also check, well, what happens if you make the other list the empty list? When you're testing, you should, and then the other thing, I should also check what happens if both lists are empty. I should check that what happens if I take the dot of the empty list with the empty list. Make sure that I get the right answer. When you're doing testing, make sure you always check boundary conditions. All kinds of, try to make sure you test for every kind of possible boundary condition. Okay. When you're working with lists, a common boundary condition to actually worry about after you worried about the empty list is to worry about the case of a 1-item list. It's not unusual to have code that works on an empty list and works on lists of more than 1 item, but actually it's possible to get a one-off error where you don't have the right answer when a list is just length 1. So you'd want to check something like that. If you were writing unit tests for this, you'd want to make sure you tested the case of lists that are length 1. Okay. All right. Now, this is just let's do another example. Let's do a famous example. Okay. Part of the notion of programming languages like this is that they allow us to have something like what are called higher order functions. Functions that take functions. Okay. A real famous example of a higher order function, just to give you a sense of what kind of things we would do, is the map function. Okay. the map function, let's see, I'm going to make this a comment. The map function takes a function f and a list like this. I'll make it 1, 2, 3. Takes a function and a list, and it gives you back a new list that applies the function to the first item of the input list, then the function applied to the second item of the input list, and then the function applied to the third item of the input list. Okay, this is turns out to be really useful. I mean, you may have heard of map reduce, which is the way Google does a lot of its sophisticated programming on servers. They have an algorithm they call the map reduce algorithm. Well, this is the map in map reduce. You have a function and a list, and you apply the function to each item in the list. See, it's a higher order function because the function takes in a parameter that's a function. Okay, so a good exercise is to write map. Okay, let's define map. Now, map is already built into Scheme, so we'll define. I'll call it my map. I want to define my map. Okay, my map is it's a function. Okay, now it takes in two parameters. It takes a function f. Now I use the letter f to mean the parameter is I'm calling the parameter f, and I call it f to think function, but it's not a typed language, so I don't declare it to be a function. And then I say it takes in some x's. Okay, so my function takes in my function map takes in a function and some x's. Okay, now what does it return? It actually is very simple to define this thing. It returns a list. So I will well, first I should do the first thing. I should condition. I need to test if what if the list is empty? Okay. What will be the result of mapping f on an empty list? You'd get a list that is empty. So you would get back an empty list. Okay. So I should check because that's the thing to stop my recursion. You know, if I get down to an empty list, the map of an empty list is just the empty list. Okay. Now, suppose I don't have an empty list. So this is my else clause. So if I don't have an empty list, this is the only other case. If I have a non-empty list, what I'm supposed to do is cons. I'm supposed to cons the f of the car of the x's. Okay, so a cons f of the car of the x's onto the map of f onto the cooter of the x's. Now, if you go up here, you can kind of see that. What is that? That is f of, well, it's f of x cons onto the map of f on the list 2, 3. So it was f of 1 cons onto the map of f on the rest of the list. So you guys kind of, you can see it was f of 1 cons onto the rest. So another way I could write that, that's a good way to write it. Okay, so that's what I did down here. I cons f of the first element of the list onto what I get back when I map the list onto the rest. Okay, now let's see. There's the cons, there's the else, then there's the conditional, there's the lambda, and the define. Okay, I think I got that right. Okay, so that compiled. Okay, so let me do some examples. Notice that this is actually very, very beautiful. The map function is one of the more profound functions in modern programming. That's why Google can build $1 billion company on the map reduce algorithm. In a minute, I'll show you what the reduce is. The reduce is not that much harder. Okay, and it's just 3 lines of code. You know, map is 3 lines of code. Now, they turned it into a distributed map. So when they do their map, this is happening on possibly hundreds of computers, but it's still this idea that map means there's a list, which is a bunch of data. There's some transformation you want to apply to the data, and you apply the transformation to each piece of the data and accumulate the result in a new list of data. So you think of the data as being broken up into pieces. You have, you know, this is how big data works these days. You break the data up into pieces, you apply a function to each piece, then you accumulate them back into whatever, a table or whatever it is. Like this might be a table and you're breaking it up into rows. You apply the function to each row, you get a new table, the table of the transformed rows. So that would be a map, okay? So down here, I could map. Now here I'm going to play a funny trick. I need to map a function on a list. I'm going to map the squaring function on the list 2, 3, 4, 5. Okay. Well, I want to map the squaring function. Well, what I'm going to do is play a trick. I'm not going to give the squaring function a name. I'm just going to define it. The squaring function is lambda x gives me back the product of x with x. There's the function. So I'm doing this in a real kind of high order functional programming way of thinking. I need to map a function. I just defined the function right there using a lambda expression. Map the squaring function on that list. Okay, should be able to run it. Whoops, what did I do wrong now? Oh, I'm calling it my map. Okay, so I should make it. I'm using my map.
And the parentheses around the X.
Where? Oh, actually, I thought they were optional when there was only one parameter. I was actually, maybe I was wrong. I thought that when the parameter was a single parameter, the parentheses were optional. Oh, and I better change this to my map too. We'll check. I thought they were optional in that case. Okay, let's see. Okay, let's put the parentheses. I don't know if, let's see. Did I do something else wrong? I did need the parentheses. I really thought, so I don't remember why I got the impression that when there was a single parameter, the parentheses were optional. Okay, so let's see. Now, did I get the right answer? If I map squaring on 2, 3, 4, 5, I should get 4, 9, 16, 25. Okay, all right. So there's an example. Now, notice it's a tremendously important piece of the whole theory of functional programming. The map function is just 3 lines of code. Okay, now let's look at the reduce one. Okay, there's the map comes with its little companion called reduce. Reduce is a little bit harder to explain than map. Okay, so here's what reduce is going to take a function and a list. Okay. Well, actually, it doesn't take a function. It takes an operator. Okay. So I'm going to write operator. Okay. It takes a function. It takes an operator. It takes an initial value.
Is there a substantial difference between an operator and a function in this language?
No. An
No?
operator in this language is a function of 2 variables.
All right.
Yeah, notice that we don't have any infix operators. See multiplication? See, it's just in the position of a function. It really is just a function, but it's a function of 2 variables. So when I use the word operator, I think, oh, that's like multiplication, addition, subtraction, I really mean a function of two variables, okay? Okay. Now, so what reduce takes in an operator, an initial value, and a list, okay? And what it does, okay, it's a little bit tricky. This reduce is actually quite a bit more. Let me see if I can figure out the best way to write this. Takes the operator Okay, I think I wrote this right. Okay. It takes init and puts it into the, it adds 4 to the init. Now, let's see. Another way to think of the operator as being, say, addition. So this would be 1 plus 2 plus 3 plus 4 plus the initial value. Okay. It's called reduce because it's reducing the list to a single number using the operator to reduce it. Okay. So it starts off over here and it adds the initial value to the last item. Then that value gets added to the next item. Then that value gets added to the next item, and that value gets added to the next item, okay? So it's reducing the list to a single value using the operator and starting off with the initial value over here, okay? Right, so it's called reduce because it reduces to a single value, okay? So this would be, this one here is treating the operator as addition, okay? So it's okay. All right, now let's try to write this, okay? Let's define my reduce. It's going to take parameters, well, okay, my reduce is a lambda that takes in an operator, an initial value, and a list. I'll call x's. Okay, so it takes an operator, initial value, and x's. Okay, and then what it's going to return. Let's see. Does that make it easier to read? I'm not sure which way makes it easier to read. Okay, okay. What's it going to do? Well, if the list is, okay, we pretty much always start off with a conditional. What do we do if the list is empty? What do we do if empty the x's? Oops. Okay, well, suppose this list was empty here. You know, what would you do over here? Okay. Actually, I think reduce part. Sorry.
Would you just return the initial condition?
I don't actually. I'm thinking that maybe reduce is never supposed to be given an empty list. Let's see. Oh, I see. Yeah, you're right. Yeah, if there's no numbers here, return the right. Yeah, I think that would be a better thing. So return init. Yeah, yeah. So if it's an empty list, just go ahead and return init. Okay. Okay. Now we don't have any other. Yeah. So now we have the else clause because we only really have to check for one thing if it's an empty list. Okay. Now if you look over here on a non-empty list, I'm going to take the operator, add it, and let it act on the car of the x's. Okay. And then, but what's the other part of the operator? The operator acts on the car of the x's, but then this part here would be reduce. Well, in our case, it's my reduce. My reduce of, well, the operator with the same init on the cooter of the x's. Okay. No. Okay. So we see. So it would be. You can kind of see it from this line here. It would be the operator acting on the car of the list. But then what is the other operand to the operator? It's this thing, but that is just reduce applied to the cooter of the input list. So you apply the operator to the car of the x's, and then the other operand to the operator is the reduction of the cooter of the list. Okay, let's see. Did that be okay? Now let's try. Let's do some examples. Okay, what does it mean to reduce using the plus operator with initial value 0 of the list 1, 2, 3, 4. Okay. Now, if you check, reduce with plus and the initial value 0 just means it's a fancy way of saying sum my list. Okay. This is actually an interesting way to say sum a list. You say reduce this list using the plus operator on with the initial value 0. Okay, so we should get 4 plus 3 plus 2 plus 1. Okay. Oh, but I'm supposed to do my reduce. I keep forgetting to define my own version. Okay, so 4 plus 3 plus 2 plus 1 adds up to 10. Okay. Okay, another example of this would be my reduce with the multiplication operator with initial value 1 on the list 2, 3, 4, 5. That'll give us the product of the numbers in the list. Okay, because that'll put a 1 here, and it'll take the times something times something times something. Okay, so that'll give us, this is a fancy way to sum a list. And this is the fancy way to take the product of a list. Okay. Okay. Which is same thing as in this case, yeah, that's like computing 5 factorial. Okay. Okay. So now what people do, here's how you make $1 billion. Okay. Okay, I'm trying. Okay, there's a map reduce command. Okay, I'm going to map the squaring function on this list, and then I'm going to add up the results. So I should get, this should give me 2 squared plus 3 squared plus 4 squared plus 5 squared. Okay. Okay. Let's see. Does anybody do the calculations real quick? Let's see. That's 4 plus 9. That's 13 plus 16, 29. Oh, 50. That's right. 54. Okay. That's a map reduce. Yeah. And turns out that somebody really smart realized that huge amounts of big data operations can be thought, this is this is a data structure of some sort. The data structure can be thought of as broken up into pieces. You're going to map some function on each of those pieces and build another data structure like that. So map takes in a list and gives you back a list. And then you're going to reduce it all down to some final answer. And if you go over, you Google map reduce as one word, and you could spend the rest of your life reading about this. It is the heart of all of what people think of as big data right now. Almost everything in big data, Apache, Spark, they're all some form of map reduce. Now, it's at a much, much higher, more abstract level than this, but the idea came from here. This is map reduce. Okay. Now, it's even more beautiful than that. There's another name for reduce. Reduce is also called fold. Okay, we are folding up the list. Okay, when we did this thing here, some people like to think of that as folding the list up, collapsing the list down to a number. Okay, so in most people in functional programming actually don't use the word reduce for this. They actually call it fold. Okay, fold is tremendously important. So you have this idea. Fold is sort of like this universal function that you could do. You could almost have just one operator in your programming language. You could have fold, and you can write huge amounts of code as folds. Okay, it's very abstract, but it turns out that you can write, there's this notion of the universality of fold. A huge amount of concepts in functional programming and in programming as a whole can be expressed in terms of folds. Okay, so here's the page, the Wikipedia page on fold. Okay, and see, one of its synonyms is reduce. Okay, it's usually called either fold or reduce. It's also got some other names. I don't remember. I have never seen it called those. I always see either called reduce or fold. Many languages call it reduce. Many languages call it fold. Okay, and then once you have fold and you combine it with map, people have realized that the two of them together can form the basis of a lot of powerful big data algorithms. And both of them are considered higher order functions because notice that one of the key parameters is a function. In the case of reduce, it takes an operator of 2 parameters. In the case of map, it takes a function of 1 parameter. So it maps the function onto the list. Reduce reduces the list down to 1 value by successively applying the operator from one end to the other. In fact, the thing we just did here is called fold right, because we folded from the right working our way left. We folded from the right working our way left. There's also something called fold left, where you start from the left end and work right. It's a little bit less useful. Most time, most folds are fold rights, and there's fold right and fold left. Reduce is fold right. Okay. All right. So that's a little baby quick introduction to functional programming. Okay. The key, one of the key things is lists and higher order functions. The ability to write functions that take other functions as parameters. Okay. Now let's look at one more example. Okay. What we haven't talked about yet is nested functions. We just talked about higher order functions. The next thing you talk about is nested functions, or better yet, nested lambda expressions. Okay. This is where functional programming really diverges from C, C++, and Java. You can't nest functions. You cannot nest functions in those languages. So I think of functions as lambda expressions. So I'm going to refer to as nested lambda expressions. But a lambda expression just is a function, so we could just easily talk about nested functions. This is where languages like Scheme and our language 8 really try to separate themselves from traditional non-functional programming languages. Non-functional programming languages very rarely allow nested functions. Okay, so let's look at a little example of a nested function. Okay, this is a real classic example. I'm going to call it make adder. Okay, I'm sorry. I'm going to define something called make adder. Okay, make adder is a function, so it's a lambda. Okay, and what it's going to take in is a number x. Okay, so make adder is a function that takes in a number, and then here's what it's going to return. Its return value is a lambda. Now this is confusing. This is not easy to read. Make adder is a lambda, and make adder is returning a lambda. This lambda is nested inside of that lambda. And the adder is going to return a lambda that takes in a parameter y, and it's going to add x to y. Okay, check. Okay, everything compiles. Okay, now let me make some examples. Let's do a few examples. Okay. Notice that this is just 3 lines of code. This 3 lines of code are really interesting 3 lines of code. You cannot write this 3-line function in C or in C++ or in Java. You can't. It's 3 lines of code and is not expressible in those languages. You can fake it in Java and C++ by doing a little bit of object-oriented programming. You can kind of do this thing, but not the way it's done here. Okay, so here's an example now. I will say define add to be make adder 2. Okay, so I've got a variable called add to. It's the return value from calling make adder 2. Okay, now I'm going to define another function, add 3, and it's the result of calling make adder with the input 3. Now, what is add to? It's the return value of make adder, but make adder gives you back a lambda. So add to is a function. What does add to do? Add to is the function that takes in a number and adds 2 to it. Okay. And add 3 is the function that takes in a number and adds 3 to it. Okay, so let's run these. Oh, I can't use add to. That's in the library already. Oh, no, actually, it's not in the library. I think I did it up here. Okay, so let me comment out him. Okay, I had my own add to in here already. So I'm reusing the name. Okay, let's see. Okay. Okay, now look at the results. What was let's see. We don't need all these other, let me just comment out that. All these tests that we were doing before, we don't need them. We can comment out this for now. See, what else, where did that 4916 come from?
The my map call.
Pardon me?
The my map call.
Oh, there's one more where I forgot to comment.
Yeah, right at the top of the screen.
Oh, there one. That's one here. Okay, let me comment, just clean up. Okay, so add 2 to 4, you get 6. Add 2 to 1, you get 3. Add 3 to 4, you get 7. Okay, now here's what's interesting. What is add 2? What if you just ask, what is add 2? Notice that add 2 is a procedure. See, this last value is that when we called make adder returned a lambda expression. So add 2 is a function. See, they use the word procedure. So we're looking at kind of a high level data structure here. This is like, remember in our language, when we define a function, we put in the environment a pointer to the function's lambda expression. Okay, so that's kind of what this is showing you. In a sense, the value of this function is something in the environment that they can't point to an abstract syntax tree. So they kind of show you that it's a procedure, and it, if you know what you're doing, you can kind of, I think actually, it says that it's something in our script. I think it's telling us that what line number it is. I think, is it?
Yep.
Yeah, so it's actually kind of exactly doing what we did in our code. It's pointing to the code.
Is there any way to get it to just print out the source code for the function? I know you
Not
can
that I
do
know
that
of.
in
Oh,
some
no,
languages like R.
There probably is. There probably is. I'm not. I haven't. I don't. I'm not someone who digs deep into the innards of this version of Scheme, but I bet there is. I bet that, but we have it ourselves right here. So add 2 is the result of having called that. So it's the result of having evaluated this guy here. Okay. All right. Now, what we have here is a lambda expression sitting inside of a lambda expression. So we have nested lambda expressions. Now, let's pull the nested lambda expression out. Okay. So I'm going to copy and paste it. And actually, what I want to do is I'm going to pull it out. Actually, let me do. I want to work over here. So let me copy and paste that over here. Pull this lambda expression out. Okay, there it's pulled out by itself. Okay, I got the balance. Nope, there it's pulled out by itself. Now, if you look at that lambda expression by itself, there's something kind of funny about it. Anybody want to suggest what's a little bit funny? Just look at it by itself.
It's an anonymous lambda expression. You never assign it a name.
Right. Okay, it's an anonymous lambda expression. Something even funnier about it.
There's no X.
Right. It's got an unbound variable in it. It's got a free variable. Okay. So the thing that's really interesting is that X is a free unbound variable. Okay. Now put them back in here. Where did X come from?
It comes from the lambda expression that wraps it.
Yeah, it's the parameter of the outer lambda expression. That x binds or bounds or closes this open lambda expression. This guy is the closure of this lambda expression. Remember, we say closure is one of the key ideas in these whole programming languages, where this one is an open expression. It's got a free variable. You embed it inside of this bigger lambda expression, and the bigger lambda expression closes this inner lambda expression. Okay? Now, think about what happens when you call something like make adder for, okay? Just call make adder for, okay? You go to make adder, and you create an environment. So let's go, let's think about the steps of evaluating this. So your interpreter would create an environment. Okay, the global environment is empty here, okay, because there's no global variables. But when you call this function, you would have to create under the global environment a local environment, okay, and in the local environment you'd bind x to 4 because you're going to call make adder with parameter 4. So then you create the local environment that binds this 4 to that parameter, okay? Then you return a pointer to that code, okay? All right, so then the return value here, so I will say define add 4 to be make adder, okay? So now when this thing returns, now I'll have something in the global environment. So after the local environment will disappear, and now the global environment will hold add 4, and it'll point to some lambda. Okay, right. So now, so I ran this line of code. When that line of code ran, it built up, well, there's an empty global environment, then it builds a local environment that has the binding from x to 4, and then when this thing returns, add 4 gets bound to some lambda. Okay, now I want to execute the code add 4 to, say, 5. Okay, now what does that do? Okay, that has to, okay, now the global environment still holds the add 4 bound to some lambda. Okay, and since we're calling a function, we have to create a local environment. Okay, that binds, now this lambda expression has a parameter y. So in this local environment, we bind y to 5 because we're calling this lambda expression now, okay? All right, now we evaluate this part of the lambda expression and we blow up. Why? What's wrong? We're executing this code, so we have to build a local environment that binds the actual parameter to the lambda's formal parameter. So we bind y to 5. Now we evaluate this. That's how you call a function. You do the binding and then you call the function. What goes wrong?
We need to link x
Yeah, we need to look up at, when we evaluate plus xy, we're supposed to find x in the environment. But there is no x in the environment. What happened to x? See, he was up here. There's where he was. What happened to him? What happens to the local environments after you call a function? Okay,
It would disappear.
it disappeared. In fact, let's look at our code. No, let me download language 7, and let's actually look at the code for evaluating an environment, of doing a function call. Because the key idea is to really, really look at how these things work. Okay, so we want to really deeply understand what it means to call a function. So let's go back to language 7 and look at the evaluator and look at how it evaluates apply. Because what we just stepped through is we were stepping through the idea of evaluating apply. Okay, so we were this is an apply. In our language, I would actually say apply. So if I turn this into our language, I would in our language I would use there here. And I would apply make adder to 4, and then the return value would be add 4 would define to be the result of applying make adder to 4. Okay, right? So I apply adder 4, add 4 to 5. Okay, and then I go over here. Oops, go over here to evaluate apply. Okay, here's evaluate apply, and you go through the steps. You have to first you have to get the function. Okay, that's step 1. You create this local environment. That was, let's see, can I, oh. Okay, so I think we can see, you're evaluating this guy. Okay, so you create this local environment. That's what's shown here. There's the local environment. Well, actually, we're up. Let's start with this one. We're doing this apply here. We're wondering what goes on over here. So you're calling make adder with parameter 4. Okay, there was no global variables. This local environment is, I'm sorry, this one right here. There's the local environment. We create the local environment. Okay, then we bind the parameter in the local environment. That's step 3. Bind the actual parameter to the formal parameter. That's step 3. Okay. Well, step 3 is to bind all of them. So then that's a for loop. This function only had one parameter. So step 3 was the loop that binds them. So steps 4, 5, and 6. Here's step 6 is add the pair. Step 4 is get the x. Step 5 is get the value. And step 6 is add them to the local environment. Okay, right? Then what do? After you've created the local environment, then you evaluate the body of the function in that local environment. Okay, right? Now the body of this function was just this lambda, so we return that lambda. But then what's the last thing here? When you return, the local environment is a local variable. So when you return from apply, that environment disappears. This environment goes away. If you were in C world, you'd say it popped off the top of the stack. You popped the stack frame off the stack. In Java, you would say the same thing. That after you call the function, its stack frame is popped off the stack. Well, this language, we don't have stack frames, we have environments. But when we call a function, we create a local environment. And then when the function, when the application is done, the local environment is just garbage collected. See, it was a local variable. So this variable is popped off a Java stack, and this environment is garbage collected from the heap. So this variable doesn't exist anymore. Then we get down here and we call apply here. Now we're gonna evaluate add 4. So we do the same kind of steps. We're evaluating add 4. We get this lambda expression out of the global environment. We get its lambda expression. We bind its variables y to its actual parameter. We create a local environment. Okay. Then we evaluate the expression. In this case, the expression is this guy in that local environment. But when we jump to evaluate plus is going to look up x in this environment and not find it. There's no x in here, there's no x in the global, and it blows up. So we have to do something to make our interpreter more sophisticated. This is, our interpreter for language 7 cannot do what we just did. It cannot handle nested lambda expressions. Okay, language 7 doesn't make sense when we do this example here. Language 8 does. So and Scheme does. Scheme makes sense of this. We just saw it run. Scheme makes perfect sense of this. And the thing for us to learn now is what does Scheme do and what does language 7 do, or language 8 do that language 7 and Java and C++ and C can't do. Language 7 is a model for C, C++, and Java. Language 7 is it's a baby version of procedural programming languages. It's a baby version of procedural programming. So it's a baby version. I'd say it's basically C without any aggregate data types. So it's C without arrays and struts and strings. Okay, so it's just, but it models applicative programming languages like C, C++, and Java pretty well. It can do most of what they can do, and it can't do what they can't do. Okay, so our language 7 we can see it can't do this because it'll blow up. In fact, we can go ahead and we can do it actually. Okay, watch this. I'm going to take this example and make it a script file. I'm going to take this example and I'm going to make it a script file in language 7. Okay, so let's see. I use var instead of, and then if I'm going to make it a script file in language 7, I need to start with a prog. Okay, and then that should close the prog. No, okay. So that's the program will define make adder, and then it will then it'll define a variable add 4. Okay, so the body of our prog is going to be a var that defines make adder, then another var that defines add 4 as the application of make adder to 4, and then the next thing we'll do is apply add 4 to 5. Okay, and then close the script file. Okay, so there's a little script file in language 7. So I'm going to save this in the language 7 folder, and I'll call it script 5. I'll call it script 5. Okay, so there's script 5. Now I can build the REPL for language 7. Okay. Okay. So here's the folder with language 7. There's the script we just wrote. I can open a command line window here, and I can Java run the language 7 interpreter on the 5th script file. Okay. Let's see. Now I may have tokenized it. Let's see. Did I get a? Let's see. I got parsing errors. Did anybody see a mistake in the script? Do I have an imbalanced parentheses somewhere? Oh, let's see.
You added parentheses around the.
Oh, yeah. In our language, we don't put those. So let's see. Maybe that was the mistake. Yeah, in our language, we don't put the. Oh, and the same thing here. We just say, okay. Okay. Yeah. Okay. So it parsed and everything. Notice that so we have make adder is I'm not pretty printing the lambdas correctly. So make adder is lambda x, y goes to, so var add 4 is the result of calling make adder with 4, then we call add 5. We get evaluate, okay. Oh, that wasn't let's see. Oh, well, first of all, this won't even parse. Our language doesn't, it blows up before the, we don't allow a lambda expression inside of a lambda expression. So it really didn't even get to evaluating this function because we broke this. We're not allowed to put a lambda expression inside of a lambda expression. I can kind of fix that. Let's see. Yeah, we're not allowed to have lambda expressions inside of lambda expressions in this language. So let's see, can I rewrite it so that I still want to have a nested function.
Would you just declare a function above and then put that function inside
Yeah, that's
the
what
lambda?
Exactly, that's what I was thinking. Let's see if that'll work. So pull this guy out. Pull this guy out and give him a name like TEMP. Okay, and then up here say var TEMP to be that thing. Okay. I think that'll more or less give us the same thing. So we define temp to hold this lambda expression. And then in make adder, make adder is a lambda that takes in an x and returns temp. Now, notice that grammatically, I'm not putting a lambda expression inside of a lambda expression. I'm putting a variable inside a lambda expression. So let's see. I think that'll maybe get around this bug or this problem over here. Oh, I have to make this fun, right? So I have to use the fun keyword here because it's language 7. So I can't use there. I have to use the fun keyword there. So now let me try it again.
Would you also need that for the other function?
Oh yeah, you're right. So this one also is supposed to be fun. Okay, yeah. So function temp, function make adder, then var add 4 is the result of calling this, and then you can apply add 4. Okay, actually, this one is also fun, I think, too. It's a function that is the result of applying make adder. Okay, so I think it should be fun, 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 then apply add 5. Okay, now let's see if we can do it now. The language is really fighting with us. There it is. There's the error we wanted, right? Isn't that, see, undefined variable x. See, now we've got exactly finally we got the picture here. See, you can see it. There's the function activation record with 5, y equals 5. There's the global environment with these functions in it. And then when you went to evaluate plus xy in the body of add 4, you got an undefined variable x. Okay, so yeah, so finally we got this as a script. So there's the script in language 7 that blows up on us. Took a little fudging, but there's the script in language 7 that when we, okay, so when we run this script here, you know, this is what we get. We get when we run that script there, you know, we get the global environment. Well, first, this here is this apply, and this down here is that apply. So there's two applies. So this apply was this one up here. If you look over here, that is this one here. This one here, see, with the binding of x equals 4. So this one here is that apply, which was this one here. Okay. And then after you do now, but then that, see, that activation record is going to go away. After you do that apply, that function activation record goes away. Okay. And then you've got add 4 in the global environment. See, there's our add 4 in the global environment. Add 4 is a lambda expression. Okay. Then you go to do the other apply. You do this apply here. And then when you do that apply, it blows up. Okay. So what is Scheme and language 8 doing so that this code, now this code will run in language 8. If I take this code and turn it into a language 8 script, it'll run fine. Let's see, we've run out of time. Yeah. So that's where, yeah, that's where we'll pick up next Monday. We're going to take this script, okay, exactly the way it is, and run it in language 8, and it'll run fine. I'll put this up on the website. You can try it. Language 8 will be able to run that script, but language 7 can't. So language 7 is C, C++. It can't do this. Language 8 is Scheme, which is, it's also JavaScript. JavaScript famously was also a baby version of Scheme. So our language 8 is a baby version of Scheme, and it's also a baby version of JavaScript. You can write this program in JavaScript, okay, but you can't write it in C or C++ or Java. Though I'll show you how you can kind of mimic it in Java. Okay, I'll show you what in Java you can do to, in a kind of very verbose way, you can kind of mimic that guy in Java. But our goal is to see what, you know, we've seen now that language 7 blows up when you run this program. Scheme doesn't blow up on it, and language 8 won't blow up. And our goal is to understand exactly why. Okay? All right. So, I'm gonna try. I'm still trying to find a pretty good reference that describes some of this idea of a closures are very weird things. They're really super important, but nobody really explains them very well. So I'm still kind of trying to find something to explain. You know, closures are the solution to this problem. We have an open expression here. If we, from the point of view of language 7, that guy isn't. there's the unbound variable. He's open. That's an open expression. That's an unbound variable. We need to make sense of that guy in better. Okay, so I'll try to find I'm still trying to find a good explanation of closure, but we're going to do it most by looking at enough examples and looking at our code. I mean, the true understanding of closures is to understand our interpreter. If you understand interpreter 7 and interpreter 8, you understand closures. Okay, so read the code for language 8. I mean, if your reading assignment really is to read the code that comes with language 8. Okay, read the evaluate. Actually, read that evaluator in language 8. There's enough comments in there, I think, to explain what's going on. Okay, so I'm going to whoops. I'll go ahead and stop sharing, and I'll just go ahead and end the class, except I don't know how to. Well, good. Now I'm stuck. We're here forever. Oh, there it is. Okay, the screen, yeah, it finally popped up. I see it now. Okay, so I'm going to go ahead and end the meeting now, all right? Goodbye.
Bye.